Okay, I guess it's recording now. Okay, so I set up some things on the board. So I'm continuing on from last Friday's lecture, where I talked about the equation that my model imposes. So my model makes a scientific hypothesis that in the main, move probabilities obey this kind of equation for some simple function g of the data and of parameters representing the skills of the player. The probability of the ith best move obeys an exponential decay relation with the probability of the best move raised to some power, the power depending on the data and on the parameters. Moreover, that this relationship should hold for some simple function g. Okay. And my model currently it's currently trained to use an inverse exponential function for this function g, which has some likeness to a softmax function in this context, in case you've heard of it, of that term, but not really exactly. And the question of the not exactly is perhaps one of the ways by which my model might be better tuned. Okay. So the function g that I want, though, has some basic properties. For first, its value at 0 should be 1. What does value 0 mean? Value 0 means no loss in value. That's a case where you have an optimal move. Maybe not the first move listed by the computer, but it could be a move that is tied in value with the optimal move. Okay? Now I'm going to show the problem that occurs when you have tied optimal moves. But for the moment, given this way of setting up the model, there is the property that I talked about last time, that moves of equal value receive equal probabilities. And this is being orchestrated by these equations, because if g of 0 equals 1, then that's saying the probability of m2, if it's equal in value, will be probability of m1 raised to the power of 1, which will just be the same as the probability of the first move. Okay, so it's legislating that feature of my model, that the values depend only on the move values. Okay. Then this function g should decrease in some smooth and continuous way towards 0. The worse the move, so the greater the loss in value, metered by these two parameters affecting the player, then the higher the function g should be. Except that what I'm really graphing here is what I call g prime. Okay. So a little bit of an annoyance. I like to picture functions going from 1 to 0 rather than functions going from 1 off to infinity. And one reason I prefer that intellectually is that a lot of the action happens in the tail. And there are issues of numerical instability. And it seems to me that I can contain them better by viewing a picture this way. But I may also be wrong. So a slight difference down here, okay, of the function value can correspond to a large difference in the inverted function value, okay, which is what we're getting here. Okay, so just remember there is this inverse relation, g equals 1 over g prime. And in my papers, you'll see that what g refers to could be either what I'm calling g or g prime here. Okay. All right, so that's an issue where I may be hiding something, but I prefer to think in terms of a drop-off from 1 to 0. So as that function g prime drops off to 0, this exponent gets bigger, and when this exponent gets really big, then a number less than 1 raised to a very high power is essentially 0. And that's a way of saying that your probability of making a very bad move is close to 0. Well, actually, that's where the issue of the thickness of the tail comes in. what is your probability of making a very bad move? To err in human happens all the time. You might think there is a basic bedrock probability of making a really stupid move at any time. But oddly enough, I have found, so I expected that the fatter tail curves would fit better. And I was influenced in this expectation by reading books by Nicholas Taleb called Fooled by Randomness and the Black Swan, in which he said that an error made by a lot of stock market forecasting and risk analysis forecasting models is that they have tails that are too thin. They underestimate the probability of majorly deviant events, which are the ones he calls black swans. Okay, so, however, my chess model doesn't show this. The fatter tail curves aren't working. And you'll see this manifested in the error estimates being too high in this case and a little bit too low in that case. So I've had the attitude until recent years that my model has merely had a Goldilocks problem. I would say one soup too hot, one soup too cold. Got to find the soup in the middle if I tinker with this stuff in blue. But as a result of what's happened in the past 2 years, I'm really now questioning what I have in black on the left-hand board. Okay. So I'm going to talk about that now a little bit. So you'll see this manifested in my code when I show it very shortly. But my model, so this is what I call a model. Oops, sorry. So this to me, this choice is what I call the model proper. And I call it, model, I call this power shares. Okay. So now let me also, by the way, the equivalent form of this, okay, is to say that the log of the probability of mi is equal to g of data. This is a little, g of the data, and I'll put the parameters down there, okay, times the log of the probability of M1. And that's the same thing as saying that the log of PI, okay, just abbreviate that over log of P1 is equal to a function that is independent of I, except for, well, I'll put in that this is GSC of this delta function VI, V1, V1, VI. Okay? So in other words, the ratio of the probability of the logs of the probabilities of making the moves, okay, is governed by a fixed function of the data and the difference in value. So this together with the sum of the probabilities equaling 1 is what I call the conversion of utilities into probabilities. And then one other final little form of this is that I want to I like flipping things around a little bit. So this is the same thing, now speaking in terms of G prime, and this is, we'll show you where I got the G prime out of this. So, so this is log 1 over pi over log 1 over p1. So I like logs that have positive signs. So I'm just negating both sides of the logarithm here. So this equals, again, this G. And I'm abbreviating again. Okay, now I want to flip this over again. So this is the same thing as saying that log of 1 over p1 over log of 1 over pi. Okay. And this is now equal to the g prime function. Now, why don't I tell you what, I'll keep the, I'll write 1 over g sc of delta I here. Okay, and then to complete the cycle of equalities and write it here, what this gives me is, this gives me the function h of pi over h of p1 equals g prime sc of delta I with h of z equal 1 over log 1 over z. Okay, so this is actually the most abstract form that you'll see in my papers. Where's the red pen I had? Oh, here it is. Okay. So this is the, so in greatest abstraction, what I am doing here, okay, is I'm saying that there is a simple function h of the probabilities, probability of the ith move versus the probability of the first move, such that the ratio of the probabilities is given by, the ratio of the h values of the probabilities is given by this curve, parameterized by s and c, applied to the difference in value, the scale difference in value of the move. And the function h that I'm using is just 1 over the log, inverse log function. So that's the abstract form. Now, this form is, with it being abstract, the fact that I made it abstract is what promotes your thinking of alternative models. Okay. And in fact, this was not the first version that I thought of. Okay. So the simpler model is just shares. So it's called shares in my program, and this is simply that p, so this is shares, this is with h of z equals z, the identity function. Okay, so this one would say that the probability of the ith move divided by the probability, so not a power of, just divided by the probability of the ith move is equal to this g function, this g prime function. And this will in fact explain, let me write out delta of v1 vi. This will explain also why I had the g prime notation originally inverted. So why I was thinking of things tailing off to 0. Okay. So that is the simplest model. I just take h to be the identity function, and it's just saying what's the proportion of the probability of the ith best move in relation to the probability of the best move. It's given by a curve like this. Okay. And the difference in value, and if you see again the basic contours, if the difference is 0, we need g prime to give you the value 1, which it does, so that would say the probability of the ith move of any equal optimal move is equal to the probability of the best move. But if g is, say, 1/10, 0.1, at the value of the difference, then that would say the probability of that move would be 1/10 the probability of the best move. And this kind of equation is still pretty elastic. If you have a chess position where there are lots of equal optimal moves, then your PI is going to be 1/20th, and a bad move that's 1/10 of the probability will be given as 1/10 of that. Now at this point, maybe there's some reasons you should see already to begin questioning what I'm saying. Because sort of like, well, so the question is, the probability of making a bad move, should it really depend on the probability of the best move in this way? I mean, one attitude you could have is, well, if you make a bad move, you make a bad move. Okay. And it doesn't matter whether it's a clear-cut position or one with many alternative moves. Okay. But the other view is, well, if you make a bad move, it's because you missed a good move. If your position has 5 good moves, then it was 5 times more likely that you might have avoided making a bad move. Whereas if your position only has 1 good move, which my model will be giving most of the probability, then that was one thing you missed, and maybe your odds really should be 5 times higher of missing it with a bad move. Now, as I said, what I haven't done, and what I admit I haven't done, is I haven't gone into the data to see to what extent that's true. So, and I was perhaps messed up a bit by the initial success. Well, first of all, the initial very obvious unsuccess of this equation, and then the relatively good success of the exponential version of the equation. Okay, so it turns out that this, in fact, fails. Okay. So I'm going to demonstrate the ways in which it fails. So I can refute the idea it fails for any, or rather I have never found, not found, a simple and natural G for which it works. Okay. Whereas this power relation, now what you can see actually, by the way, let me tell you what this equals. So then you'll see the relationship. So this is the same as letting G prime of SC delta I be the share of utility of move on mounting. So where a full share equals 1, okay, and then averaging the shares. Okay. So when you have a championship hockey team or a championship baseball team, here's how they divide the prize money. Okay, the way they divide their prize money, because you have players who are on the main roster, but then you have alternates, and so you have pitchers who were in the minor leagues and came up for some of the year, and you have players who maybe were traded to the team in mid-season or played a relatively minor role. So the way they work it is they vote all the players' shares. So the main roster players each get a full share of 1, and then other roster players might get a half share or a third share or a 40% share. And then to dole out the prize money for winning the World Series, you average the shares. What's your share in proportion to the sum of all the shares, where we don't necessarily prescribe what the sum of the shares may be. I mean, there are 25 main players on a baseball team at any one time. but you know, the total shares might be 67 or so, and the sum of the shares might come up to, with the half shares and third shares, might come up to a number like 42. So then you'll split the money 42 ways, and some people will get a full share of that, etc., like that. So this is the same process. So if you have each move given a share where the shares don't add up to 1, and the optimal move gets a share of 1, and then other moves get whatever relation is implied by this G, it won't add up to 1, but whatever it adds up to, you just divide, just normalize the shares, and this is saying that's the probability. Okay, it's the simplest idea you could think of, and it doesn't work. So what people have found in big data is that what works better in practice is to do a softmax average of the shares. So if you have an ocean of shares, you're reflecting a reality that the person who numerically you're giving a 1/3 share or whatever data effect is actually contributing less by some sort of exponential function. So you want an exponentially averaged form of the shares. Okay? And that's exactly what the softmax is. The scientific reality of the softmax function is that it works better as an average than the, and approximately, but maybe not exactly, that's what this is doing. So have you discussed softmax, the scientific principle behind it, or the reasons why people use it? Has that come up in 574, your other courses? Okay. Nobody's heard of that? Oh, okay, all right. Okay, I was curious. All right. Well, I don't feel bad because I was ignorant of it for many years after I discovered that the power shares worked better. Okay. But as you see in my program, I've put out hooks for tinkering with other possible models. So this is what I call a model. And as you see, I've made an attempt to reflect a logit model and a softmax model more directly in my equations. But it's sort of like even that maybe is not the primary issue of the fitting. The primary issue is really that I maybe should not be trying to impose such a law at all, but should do a more liberal, less constrained regression on the data. Okay. But anyway, regardless of this, let me tell you what the process. Okay, so the implied process. Okay, so the implied process of this setup has 2 levels. Okay. Okay, so level 1, okay, is that given the data, and given parameters, given values for SC, okay, solve the equations P1, then get P2, P3, on up to PM. Okay. So, regardless of which model we're using, and now I will circle the one that I'm currently using in green. Okay. So given the data and given values for the parameters, we have L equations and L unknowns. This is L-1 equations because, so this is for I equal 2 up to L. That's L-1 equations, and then this is the last equation. And one thing to notice, by the way, is that the last equation is the only interaction between probabilities of different moves. The main equation for any particular value of I is involving just the ith move and its data and the probability of the first move. So it's basically like every move gets a share in relation to the share of the full share of the best move. And then you're normalizing the shares, making the probabilities sum to 1, however you determine, whether you determine the probabilities by a power or by just simple ratio. Okay, so then you solve the equations for P1, P2, PL, and then this generates predictions. Okay, so this generates predictions, or projections, I should say, of my quantities MM, EV, and SD for a player with characteristics, I'll say formal player, P of SC with characteristics SC and whatever other parameters I might have. Okay. Then the second level is we fit S and C using these projections, okay, given data, given a player's games, okay, fit SC, to make the projections fit the sample. Okay. So this is unbiased estimators. Okay. Okay. But lurking in the background is 2 prime, which is to fit S and C to maximize product from t equals 1 to t of the probability of the played move m I star at time t. Okay. And this is maximum likelihood estimation in this case. That's the other idea. Maximize the track record of the moves that were played. Okay, so that's what these 2 processes are. So this is option 18 in the menu, called a performance test. And this is option 17 in the menu, a fit. Those are the 2 main operations in my model. So I'm now going to show you my program and what I did over the weekend is I updated the data and prepared the directory on Metallica completely for your use. And I added a nice feature based on last Friday's lecture, and I reverted my program. So I put my program in an earlier, more robust state as far as the fitting goes, where we're just going to focus on S and C for now, and then I'll motivate the reason why I felt compelled to consider the other parameters. Okay, can someone dim the lights a little bit? We go into demo mode now, and the camera may be focused to be a little bit further up, more up here. Okay. All right, so now I have set up this folder now. I moved up the previous year's work to a directory you can still view called Prev. Okay. I've enabled write access on all these directories, so I'm not forming a special group or of people in this course, but you're on your best behavior as far as not messing it up for other people. There was one such case, but it was quite accidental last year. So there are three main subfolders. There's the one called Moves, which is my entire training set, and I've just updated it, and I cleaned it out a bit. So I updated this to include all the data now from 2017. Okay, so this has data duplicated taken with two different chess programs. The chess program Komodo 10 and the chess program Stockfish 7. And so what these files are, let me emphasize Stockfish. They're the entire corpus, entire training set of moves from all years in which the rating system has existed. And they're in a format that gives the chess position in what's called Fen notation, and then different values. It gives the move number. Now all my data starts at turn 9, and it's not because turn 9 is what I think of as out of book. It's that I don't think computer values, it's my best stab at the threshold at which computer values become relevant. Computer values of the opening moves I don't think are very relevant. But of course it depends on the game. There are games where the computer's value at turn 3 is very important. There are games that are booked through move 30. But my sense is move 9 is the best place to make a cut. Okay. And then this 0 is the number of repetitions. This is the result of the game. These are the ratings of the players, and notice that the ratings of the players are all within 10 of the level 2275. Okay, so here was a player rated 2271. Then this is the program that I used to take the data. This is the engine's move and the value of the position, and this is the move the player actually played. And finally, 11 is the difference of value in hundredths of a pawn. So the units in these are centipawns, hundredths of a pawn. And right away, by the way, there's a lot of weirdness that goes on with the data. And the weirdness is that the values really do jump around. So don't necessarily, jump around. Don't necessarily look for consistency here. So the poor move put the value of the position down to 9 centipawns. But when the computer got thinking on the next position, it revised that down to a 1 centipawn advantage for white. All of the signs mean advantage for white. So in fact, this game wound up being won by black. At the end of the game, the computer decided that black was almost a queen ahead, minus 829. Queen is worth 9 or 10. Okay, so 0-1 means this game was won by black. Okay, so this has my entire training set. This game played in 2006. There are games going for 2275 level. Let's see if we can find. Okay, that's actually that's 19 points ahead. I was looking for the year 1992. That's game number 1992 in the file. Maybe at 2275 level, I don't have games going back to 1992. There are fewer games were collected back then. Okay. So that's this. Now this is what you'll mostly do for warm-up exercises. Okay, this is the easiest data to work with, but it lacks the context that my program is using. In particular, what it lacks is it lacks the values VI of the other moves besides the optimal move and the played move. So for that, we have the AIF directory, and this is where the data to be used in the seminar resides. And I added, over the weekend, I added the data for 2017. So I finished taking my data for 2017. It was, by the way, several gigabytes of data. So, and I try to economize on my footprint, so I deleted several gigabytes of data. I backed them up on my home PC that was there for the tests of the fraudulent Russian tournaments that I bought. Maybe I should say it on camera, but whatever. It's going to be known very soon. So that's what occasioned me to add these files, and therefore I left the ones from 2014 there. So we have files for 4 years, and that's also what I fit. Okay, so these files have the data in full form, although my program is currently set to use only the rightmost column of moves, whatever column that is. So here's the case, the base depth is 20, but I allow taking depth up to 30, depending on how many nodes the program goes through. So what it really takes is it goes to 200 million nodes and then finishes its current depth. So here it was on depth 21, but in this case, it got over 200 million nodes and only got to depth 20, which is the basic depth. Here again, depth 20, but if we go to the end game, let's see, so 23, space, 24. There's a case where it got more into the end game. Actually, there's still queens on the board, but here it got up to depth 27 before it went over 200 million nodes. Okay, so it's always using the values. This is a black move, a case where black had to recapture a queen. In fact, that's what it was. Other moves would have instantly lost the game. Okay, so this is the main data that's being used by my program, so it's all there. As I said, it's multiple gigabytes. Then, finally, there is the directory IR. In fact, let me, yes, no, but I want the IR code to be here. Okay, so let's see, actually, let me copy, let me make this consistent. Okay, so IR is the executable which I just produced this morning because I decided finally to be less ambitious and to put in the regression. So IR, lowercase IR, is the executable of my C++ code. Now in the directory, IR itself is my actual C++ code. And if it comes to editing it, it's currently all in one file. Oh no, I have other files here, the H files too. I actually use a system, I have scripts that can pack it all into one file and compile it that way, or unpack it into the separate .c, .cpp, and .h files. So the code is written to work either way. So we'll use this directory as and when we get to a stage where you guys are helping me or doing it yourself, rewriting the code and trying other equations. Okay. But for the moment, the work can live here. Now, so let me run the program. Okay, so this is, this is something also, by the way, don't take what I do too literally. Grandfathered from almost 30 years ago, I have my path set up so that it looks in the current directory, but you guys don't. So to invoke my program, you'll have to write /ir unless you change it yourself. But don't be mystified if I sometimes forget to do that. Okay, now, what it does is I always have an initial yes-no question before my program begins, one little hesitation. And what this is telling you is that the program has a built-in lookup path for data. So if you don't specify a path, it's going to use this path, which is the AIF directory that I showed. Okay? And my program uses a basic reference set. Okay? And you can think of the SF7turns.aif as a standardized test of about 8,400 positions that I use as a fixed reference. And so it's just saying that you're going to use that as your fixed reference for the moment. There are options to change it, but there's actually, I don't think there'll ever be a reason you want to change that. The SF7 means that this is using Stockfish 7. So we'll say yes to that, and now it's going to go through a lot of reads. So it takes a while to read and create objects. So there's like a 15-second delay. You'll see a lot of feedback on the screen. And what it's creating is creating basic filters for moves. So what my program also has is database capacity for moves. Database capacity, in fact, enough to identify one single move in a game. Okay, so what I've left room here on the board to plot, and what I'm setting is an exercise for everyone by which to get accustomed to my model is what does my model imply as the item characteristic curve of any one move. Okay. All right. So now let's see. So these are my programs, and I don't know how self-explanatory or not my model is. Basically, though, the idea is that options 1 to 4 touch gingerly. Options 1 to 4 are the things that involve changing the model and its settings. Okay, so I reconfigured this to have settings that would be simplest for using what we have. You can sort of ignore option 1, in fact, completely. I had option 1 was for when I was comparing the power shares and the shares model. So a trial involves a model, but I decided to allow you to change the model of a trial anyway. So I'll go into option 2 and show you what's there. So these are the models that I've been talking about. Shares is the original one. AI is is just standing for the value G that you get. So power shares is the model selected, saying the probability, the best move, raised. You actually wrote 1 over AI there. But you see there's my attempt to do softmax. I'm not sure I'm actually right about that. Notice that this is doing an express exponentially weighted sum over the shares. Okay. So I'm saying the power shares is kind of like that, but it's not quite numerically the same thing. Then there are various other attempts to use logistic curves, but I can't even tell which is the right one. All right, so let's stick with the power shares. If you go into this, there are some questions you have to do that are for legacy reasons, but okay, we're back to where we were. Then 5 allows you to add more game turns. So someone pick a multiple of 25 between 1500 and 2800. Yeah, pick a multiple of 25. All right, I'll nominate 1775. Okay, someone else pick a year, 2014 through 2017.
2015.
2015. Okay. So now what I'm going to do is I'm actually going to clean out. So the program comes equipped with the reference set as the basic thing to analyze, as well as its use as reference, which it always has. Okay. So now the path is already set. So we chose the rating level 1775 and the year 2015. Then you could put wildcards, but let's specify Stockfish 7, not Komodo, and the file ends in the suffix AIF. Okay, so hit return. Now what the 6 is, it cleared out the previous terms, and 5 is adding more terms on top of that. So now it's reading that file, and it's loaded in, and it now tells you that it's loaded in 5,538 moves from this set of games in the year 2015 between players, each rated within 10 points of 1775. However, about 1,200 of those moves have been filtered out. Okay. And what got filtered out is it filtered out any position that was repeated later in the game. So that's a nudgy issue in chess, which I allude to very briefly in the survey paper that I gave you to read. That it causes complications for chess engines because they give value 0 on the first repetition, but the rules of chess say only on the second repetition, and it's a mess to correct it. So I just screen those positions out. And then there's this weird filter. What it's doing is it's keeping moves only if the game was relatively close, either at the current turn, the previous turn, or the next turn. Where relatively close means neither side more than 4 points ahead. It's actually a change. I used to use 3 points ahead, but now I'm using 4. Okay, so what it's saying is that in these games, about 1,200 of the positions were ones where one side was more than 4 points ahead, so easily winning. And that causes a lot of noise in the model, and also I have a reason to presuppose that a cheating player would stop cheating when the cheating player could see the game was clearly winning. Okay. All right, so that's what's loaded. Now, so let's actually first run a fit to find, so this is my fitting menu. This kind of scrolls off the screen. Here, now I got everything on the screen. So what's here? This is actually a little laboratory for doing statistical fits. And it's creating a loss function that has contributions from these various sources. And then it's going to, I set it up to minimize the loss function. So for maximum likelihood, I'm inverting the probabilities. Okay, so what this is saying is use for my loss function the difference between the sample and the projection of the frequency of playing the first move. That's my test. And then what I call fall off, I could call error, but error is more judgmental. So I sometimes refer to this as the average error, but this, so I should change the program to say this is the scaled difference instead of the scaled fall off. Okay, but this is my SD, my scaled difference. I'm not including equal top value in the test at the moment. So just including those two things. And I have 2 parameters, just S and C. These other parameters are turned off. Okay, so in your version of the program. And there's a starting point for the nonlinear fitting that I'm using. Okay. So now I can just go. So there's on menu option 35, also called go, but I have the idea that I want to name things. So I want to call this AA 1775 in 2015, Stockfish 7, and then with 2 parameters, W2. You don't have to use my name, but if you see output from me, that's the kind of naming scheme that I'm doing. Now what this is doing is it's doing Nelder-Mead simplex algorithm, which is a minimization method that doesn't need derivatives the way Newton's method does. Because I don't know how to take derivatives of these equations. Maybe if one of you figures out, that would not only be a project, that would be a publication. Okay. Now, what happened is I took data that was supposed to be 1775, but the measurement I actually got was 1704. Okay. But 1775 is within these narrow error bars or my expanded error bars. So the 1704 came from a linear fit that I did, that I executed. So this is just mean a residual. This is a residual that's a little low. And actually, owing to some nonlinearity, the residuals you get will mostly be low. There's a little bit of skewness in the current fit, okay, that I have. I haven't tuned it up. I don't even necessarily want to tune it up, because I don't want to imply greater accuracy than we actually have at this point. Okay, so that's what we got. Now the other thing, so that's option 1. So actually, that's element 2. So actually what I should have done, well, let's see. Yeah, I actually did things in the wrong order, but hey, I have this saved to a menu. So let me actually do things in the right order. So if I want to put settings for the parameters, then I call that a trial spec. So trial spec has these values for the parameters, okay, and it has other things. It has the curve, and the curve that we're using is completely the inverse exponential function, okay, what's on the board in blue. But let's go into the curves menu, so menu item 1, and you see there are all of these other curves, including these 2 inverse polynomial curves. That's what I've done underneath. Then there's an attempt to fold a bell-shaped curve, and there's an attempt to fold half of a logistic curve. So if you take the S-shaped logistic curve and fold it over, so if you turn it upside down and then declare this to be your value 1, then you get a curve that sort of looks like that. So when I say folded logistic curve, that's what I've done. I've turned it upside down and folded it in half. And then there are these hyperbolic functions are supposed to be related to logistic curves, but they're all a little different. And then there's freaky stuff, and then there's something supposedly coming from IRT itself. But anyway, let's just stay, and we can adjust the weights of all these curves. So you can mix and match, maybe find a Goldilocks curve, but I'm just going to stay with inverse exponential, so it's